Chapter 4.3. So this is a lot like the last section. However, the functions that we're going to be looking at are not necessarily linear. Okay. A nonlinear function, if you need to, if you need this definition, write that, is a function whose graph is not a line or part of the line. So this chart is a really good example of the differences. So a linear function is something that obviously looks like a line. Okay? A nonlinear function is something that is not like a line. So it's got some kind of a curve in it. It could be two lines that come to a corner, and then one line, and then it shoots off to another line. Anything that it's not one continuous line is nonlinear. All right. It's not that it has to go forever. It could be part of a line, so it could only go from this point down to this point. But if it has any sort of a curve, or if it stops and shoots off into another line, that's nonlinear. So here we're going to, once you get used to this, you may be able to tell the difference just by looking at a chart, a graph, a table. But for right now, we're going to graph some of these to show you the difference. And so we want to graph these functions and figure out whether each function is linear or nonlinear. So I'm going to start over here with pizza area, and I made a graph already. So the x-axis represents the radius, and the y represents the area. So when the radius of a pizza is 2, the area of that pizza is 12.57. So 12.57 is going to be right down there, right about there. When it is 4, it's up at 50.27, so here's about the 50 line. When it goes to 6, it shoots up to 113. That's about right there. Looking kind of linear. When it hits 8, it shoots up to 200, which is about there. And then 10 goes up to over 300. And if you notice closely, we get a little bit of a curve to it. It starts to kind of curve. It's kind of as good as I can do. But it has a slight curve to it. So it's not looking linear. Okay? Again, linear would be like a straight line, and this has a slight curve to it. So this one already we know is non-linear. How about this one? We have 2 and 8, so this is the cost of pizza. So if we have 2 ounces, that costs 80 cents. Right there. 4 ounces is $1.60, so we're looking right up there. 6 ounces is $2.40, so $2.40. This is $3. Oh, sorry. Read my graph. So $1.60 is right about there. $2.40 is right about there. At 8, it's $3.20, so we're looking right about there. And with 10 ounces, we're at $4. About there. And this you can see is very linear. This is a nice straight line. So this one is a linear function. So again, the difference. Linear obviously makes a line. Nonlinear has some kind of a curve or not a line that continues. It has like some kind of a corner in it. Table below shows a fraction A of the original piece of a paper. Of the original area of a piece of paper that remains after the paper has been cut in half n times. So what we're saying is you take a piece of paper and you cut it in half one time. what's left is 1/2 of the paper. Okay, so you cut it, and half of whatever you cut you throw away, and the other half you keep. So if we do this, this is what it's going to look like. Here's our piece of paper. You cut it. This half is done. Now you have this left. You cut it in half. This part is done. So now this is 1/4 of the original. Cut this part in half again. This is gone. This is 1/8 of the original. And again, this is 1/16, and it goes on and on and on. So we want to graph this. All right, so what I did is I created a graph, and I labeled my y-axes in 1/16 of the original piece of paper. So what I have to do is I have to convert these to 1/16. So one cut, 1/2 is 8/16, right? Same thing. 8/16 is 1/2. After 2 cuts, we're down to 1/4. 1/4 is 4/16. After 3 cuts, we're down to 1/8. 1/8 would be 2/16. And after 4 cuts, we're at 1/16. And if you look at this, we are looking a little bit curved, aren't we? We got a little bit of a curve in there. And this actually kind of goes up a little bit. And so this is a nonlinear. And if you see this would keep going, and would keep that kind of curve pattern to it. So this is a nonlinear. All right. So how do you represent these? So this is a little bit trickier than linear. So this table shows the total number of blocks in each figure as a function of the number of blocks on one edge. So this has 1 block, 2 blocks, 3 blocks wide. And then this is the total number of blocks. So 1 block wide is 1 block. 2 blocks, you go 2 over and 2 up. You get a total of 8 blocks. When you go 3 by 3, you get to 27. What is a pattern you can use to complete this table? Well, you could draw it all out, or we kind of look for a pattern. So what do you notice? Well, when we go 4 over by 4 up, what do we get? 4 by 4, we got 4, 8, 12, 16. So we got 16 of these. And then we have 4 of these deep. If you think about it this way, we have 1, 2, 3, 4 blocks deep. So we have 4 of these little squares deep. So 4 times 4 is 64. And the same holds true for 5. When we go 5 by 5, there's 25 right here. And then if we have 5 of those deep, that's 125. So what's our actual, how do we represent that as an equation? Well, all we did is we took whatever number we had 3 times. So we took our x times x times x, which is the same as x cubed. And so that is how we represent that as an equation. What about the number of new branches in each figure of the table? Well, the first one we have 3. Second one we have 3 here, 3 here, and 3 here, so that's 9. The next one has 3 here, 3 here, 3 here, but then we did that 3 times. So if you think about it, the first time we did just 3 of them, and then we had 2 3s, and then the third time we had this right here. Each little branch here is 3 3s, but there were 3 of those, so it's another 3. So what's our pattern? We're just taking 3 to the, here it's 3 to the first, here it's 3 squared, here it's 3 to the third. So our pattern is 3 to the x. So this one would be 3 to the fourth. And 27 times, 3 to the fourth 81, and 3 to the 5th is 243. All right. Last one real quick. Write a rule to describe a nonlinear function. So again, write a rule that represents a function. We're essentially looking for an equation. This, what I would suggest is you take it and you try to put it into a table as an ordered pair. So these are your x's and your y's. So that's 1, 2. This is 2, 4. This is 3, 8. And this is 4, 16. And this is 5, 32. Now, can you notice any kind of a relationship? So this is where it gets a little bit trickier because it's not very obvious what to do for that. So what they suggest is try to come up with ways, how do you get from 1 to 2? What are things that you could do? Well, you could say that y would equal whatever x is times 2. So what I'm saying there is, how did we get to 2? We took 1 times 2. Okay. What else could have we done? Well, we could have said we just added 1. Right? Didn't we just take x plus 1? So that's another possibility. And the third way is we could have said we just took the number 2 to whatever power this is, which is x, which is 1, right? So those are the 3 ways that work for this first one. Okay, what works for the second one? Does this work? Y equals 2x. Yeah, if you take 2 times 2, that gets 4, so that still works. Does y equals 2 plus 1 work? If we take 2 and put it in there, 2 plus 1 is 3, so that no longer works. How about this one? 2 to the x. 2 to the second power. 2 squared is 4, so that still works. Okay, so we're still alive with 2 of them. Let's keep going. Let's try this one. Does y equal 2x still work? 2 times 3, does that equal 8? No, that equals 6. So that one no longer works. This one didn't work last time. How about this one? If we took y to the 2x, what's 2 to the third power? 2 times 2 times 2 is 8. That still works. Does it still work for this one? See, all we're doing is 2 to the first equals 2. 2 squared equals 4. 2 to the third equals 8. Does 2 to the fourth equal 16? You bet. And how about 2 to the fifth equals 32? So that is our rule. What's the rule for this function? Y equals 2 to the x power. That's the type of stuff that you'll be doing. Make sure you ask any questions if you have them.